Thank you for the introduction. I thought I'd talk a little bit about some insight from industry, working on the industrial side of things. Before we get too much into that, I have to show this safe harbor statement that essentially says that I am not going to commit to anything for our products relating to this presentation or something like that. Okay, so first thing I'd like to talk about is evolution. GC has evolved a lot over the years in OpenJDK as well. We have the serial collector, and it's old now, but it's still pretty good for constrained environments where you don't have many hardware resources. And then we have the parallel GC, which is still pretty good when it comes to maxing out throughput, but comes with latency concerns. We had CMS, concurrent mark and sweep, but retired it in favor of G1, which is more of a balanced collector that tries to find a sweet spot between throughput, latency, and memory. And that makes it a pretty good default collector. It's not the best at anything, but it's also pretty good at everything. And the latest incarnations are concurrent collectors. We have Shenandoah and ZGC. And here the aim has been primarily reducing latency and improving scalability. It's been great to see all this innovation, and I'm also thankful to the research community for playing a big part in developing new GC algorithms. And since the behavior of the GC has a big impact on the behavior of Java application, it is pretty important with all of this innovation. Evolving GC, I think, requires planning. It turns out that building a production garbage collector and taking it all the way into production and sorting out all the performance issues and stuff takes about 10 years. And during this time, the market has time to change, and there's a new situation, and suddenly you find that, oh, well, now we need another garbage collector, and so on and so forth. Happens again and again. And it turns out that there isn't really one GC to rule them all, so it's pretty important to consider the different trade-offs, and it takes time to get it right. And because of this, one of the key aspects to succeeding in the long term is planning for the unexpected garbage collector that you will find down the road. And it might have entirely different constraints. So one of the things that you really want to avoid in order to get that is exposing GC implementation details. And for example, the address of an object, don't expose it. The field addresses, even the offsets of fields or the size of objects, the format of pointers, all of these things, by exposing them, you're locking in the GC in some kind of GC jail where it cannot evolve. And it might make some native call 10 nanoseconds faster, which seems really great in some micro benchmark, but the reality is that you've locked up the GC here, which might be a much larger problem. And I think that one of the successes of garbage collection in Java really is because we've done a pretty good job from the start of encapsulating the GC implementation details. With the Java native interface, there's a level of abstraction. You calling functions to mutate and the state of objects and things like that. And Project Panama has adhered to similar constraints. We're not exposing things, and this allows a GC to evolve. And also inside of the JVM itself, being part of building something that I call the Access API inside of Hotspots. It's an API for performing memory accesses with declarative semantics. So rather than saying do a pre-barrier or post-barrier, whatever you think that a GC needs, instead it's more high level. It's a load, it's a store. What's the memory model? Is it sequential consistency, or what kind of memory ordering constraints do you have? As well as if you have a reference, is it a strong reference? Is it a weak reference? This sort of thing. So it's an API for communicating semantics from a front end, what is my expectation here, to a back end. And this allows building new garbage collectors. And yeah, I'd like to just do a little shout out. I appreciate the efforts from the C, Ruby, and Julia papers that we saw this year trying to break out of this GC jail. It's been fascinating to see. Yeah. So I mentioned that it takes 10 years to get a GC all the way into production and make it good. So then you might wonder, why is it that it takes so long? You think, yeah, I have this simple algorithm, and you're going to mark some objects and throw away some garbage. How hard could it be? And it turns out that the GC interacts with a lot of systems within the JVM. You have JVM TI, debuggers, you have monitoring serviceability, and there's 3 different just-in-time compilers and 2 interpreters, the runtime, and the JITted interpreter we have is JITted for multiple different processor architectures, and then you have to implement stuff for all the different processor architectures. And that goes for some of the JITted code as well. And then you have things like class loading and unloading that interacts with the GC, and reference processing. That really complicates things, especially when it comes to concurrent reference processing. Once you've gone through all of that, then now we start having startup and warm-up mechanisms to start a VM faster. And once again, there's a whole bunch of GC interactions. Even virtual threads has a lot of GC interaction. It was actually most of the work was just dealing with all the GC interactions. And then, of course, other than dealing with all these issues, you still have a lot of corner cases to think about in terms of out-of-memory handling, and why is this performing 1.3% slower in Windows in some random build, and these sort of kind of boring issues, but things that need to be sorted nevertheless for a production garbage collector. So because it takes such a long time to build a production garbage collector, it's increasingly important to think about the problem domain and make sure that if we're going to spend 10 years building something, it better solve a problem. So while it's still good to make a brilliant solution for a small problem, it's more important to even have a primitive solution to a big problem. So ideally, you want the sort of solution domains and the problem domains to intersect so that the thing you're solving is a genuine problem. And on that note, I think it's worth thinking about the environment, because in reality, people are running in some specific environment. And since each garbage collector has a trade-off, you have to consider what kind of deployment would I like to optimize for here? What problem am I solving? And, well, then it comes to memory scaling. And let's talk about that a little bit. A lot of the JVMs run on machines with DRAM. You have some kind of computer, has some DRAM. And the main thing to consider about DRAM is that it isn't SRAM. It's really cheap. And I think the price here of DRAM really matters for the problem domain. So I've incorporated here a little chart showing the DRAM price per gigabyte since 20 years back. And as you can see, it's sort of converging on the very low end there. So let's look at some environments. If you have a laptop at home, maybe you have a MacBook or something, you might get between 16 and 24 gigabytes of DRAM. And this, if you scale it to the number of cores, is 1.6 to 2.4 gigabytes per core. And even an iPhone has 1 gigabyte per core. And with a Samsung Galaxy nowadays, you get 1.5 to 2 gigabytes per core. Of course, there's some more smaller devices. For example, the smallest scaling you can get for a Raspberry Pi 5 is half a gigabyte per core, but it scales up to 4 gigabytes per core. Apple Watch, half a gigabyte per core. Usually these small devices isn't really where we make Java deployments, but they're there. but the most common deployment type is to some form of computer. And nowadays, people really like using someone else's computer in the cloud, and we have various cloud vendors, and I got, in this example here, I have listed Oracle, Amazon, and Google Cloud, and they all have AMD, Intel, and some kind of ARM instance that you can buy. And what they have in common here, as you can see, is that you sort of get 1 gigabyte per core at minimum. It's not possible to buy less than that. For some instances, for example, here we have the Amazon Cloud, Intel instances, it's at least 2 gigabytes per core. And Google Cloud Intel instances looks like it's also 2 gigabytes per core. And there are even some names for this that, if you talk about compute-intense instances, they're the minimally scaled instances that have 1 gigabyte per core. General purpose instances have at least 2 gigabytes per core, and memory-intense instances have at least 4 gigabytes per core. And now, of course, you have containers. People run things in Kubernetes and things like that. We have smaller amounts of memory, but then you also have smaller amounts of cores. Because the scaling is still based on these machines, because you're running Kubernetes clusters on these cloud machines. And in the Oracle Kubernetes engine, seems like the smallest container you can buy is half a gigabyte of DRAM, and that's using only 12.5% of a core. And it's the same number for Amazon's Fargate, which is a similar Kubernetes engine there. And so you might be wondering, why is it that we get at least 1 gigabyte per core? Well, if we look at the different shapes we can get in the Oracle Cloud here, this is the cost distribution if you're buying 1 core with 1 gigabyte of memory. That it's, as you can tell, it's predominantly CPU, the blue stuff, that costs, and the green is memory. So at this scaling point, even if you go less, the overall cost saving is pretty small. So that's why smaller memory scaling than that isn't really available. So my main takeaway here is that if you're deploying a Java application to some kind of computer, then you can expect a reasonable minimum heap sizing or memory availability of 1 gigabyte per core, right? So let's talk about moving tracing GC. In OpenJDK, all of our collectors right now are moving tracing garbage collectors. So there's Serial, Parallel, G1, ZGC, and Shenandoah. And the thing about moving tracing collectors is that since you're only paying for the live stuff and not for the garbage, that means that you have a trade-off between memory and CPU. So you can choose which one you pay for. And remember then that memory is pretty cheap. So I sometimes joke about how DIMMs are the best hardware accelerators for GC. You just take a DIMM and plug it into the heap, and suddenly all of your GC worries just go away. And with the 1 gigabyte per core scaling that you get at least, it turns out that's quite a lot for a lot of workloads. So something that I sometimes see maybe a little too often, a story being told, is you have an evaluation, you have a 16-core machine with 64 gigabytes of memory, and then you're trying to run with number of benchmark threads equals to the number of cores, so you're utilizing all the CPU. But the minimum size you could run this thing on was 149 megabytes. And the way that we're exploring the CPU versus memory trade-off is by multiplying this size by 6. Then we stop there because 6 sounds like a lot. But, and with that rationale, you'll often find that concurrent GC seemed like a bad idea, and the rest of the OpenJDK collectors also perform quite poorly. And then there's a proposed solution that improves on this GC overhead, and it looks great. And you can sort of visualize the reasoning here. It looks compelling that on the left-hand side there you see the minimum heap size of 149 megabytes. And when you add on 6 times more memory, you see all the wasted memory there in orange. Sort of looks like a lot. But unfortunately, I think what happens in reality is that we've tried using between 0.23% of the available memory to 1.36% of the available memory. And at the same time, we've been using 100% of the CPU resources. And this gives us a pretty significant blind spot for what happens if we scale further. And spoiler alert, it does change quite significantly if you use only a handful or maybe 10% more of the available memory on the machine. So yeah, I think this is a bit problematic and a bit of an error mode to run in this way. And we can optimize further for this mode, but I'm not entirely sure why. So from my perspective, looking at this, what I see is, visually speaking, more like this, that we have, this up to 6 times the minimum heap size. But for me, with the sort of deployment kind of perspective, the wasted memory isn't the garbage inside of the heap, it's rather the unutilized memory on the machine that isn't being used. So the thing about having a two-way trade-off between CPU and memory is that you're always wasting something, right? Because if you're wasting less memory, then you're typically using more CPU instead. And since memory is cheap, it's pretty useful to be able to go in the opposite way and wasting more memory to save CPU. So in a way, wasting memory and utilizing memory is sort of the same thing looked at from different perspectives. So an alternative way of looking at whether you can save memory in your system in terms of actual cost is to check what happens if I run with 1 gigabyte per core, 2 gigabytes per core, or 4 gigabytes per core. Because if you can take your deployment off a 2 gigabyte per core machine and go to a 1 gigabyte core machine, you might be able to save 5% cost, which is a real win. So my point here is not just that the levels are discrete, but that the lowest level is still pretty big. So we take the same experiment and use the 1 gigabyte per core scaling. It sort of looks like this still, that we end up not using more than 5% of the machine capacity. So some main takeaways about this is that when you have a moving tracing collector, garbage is something that makes it CPU efficient. And this is great when you have memory availability. And typically you have at least 1 gigabyte per core if you deploy into some kind of computer. And I think this is one of the successes of moving tracing collectors and why all of our collectors are moving tracing collectors in OpenJDK. And when it comes to this minimum heap sizing, to be a bit wary of relative differences. For example, 5 megabytes compared to 50 megabytes is a 10x difference, but 50 megabytes is overall a small amount of memory, and that utilization isn't necessarily waste. Let's talk about CPU scaling a bit. So when you add on more cores to a system, what happens when you have a garbage collector is that you induce more allocation rate. So if you have 1 core, might be allocating at 100 megabytes per second. With 10 cores, we're talking about a gigabyte per second. So it really adds on allocation rate. And the allocation rate scales the frequency of GC as well. So if you have 10 times more allocation rate, unless you do something about the heap, you're going to have 10 times more frequent GC. And that's in turn affects the amount of work that we have to perform in per unit time. So 10 times more GC, well, that means 10 times more GC work as well. So just playing around with some mathematical modeling here, if we have a 298 megabyte heap and half of it is live, and we have 256 megabytes per core allocation rate, then you can see here that at one core we have, well, less than 1 GC per second. And as we scale this up to 64 cores, we start getting to over 50 GCs per second. So that means you have to GC like every 20 milliseconds or something to keep up, which is starting to become problematic. And since this is just a bunch of math now, there's nothing stopping me from scaling it further because there's no cost attached here. So if you have over 30,000 cores in the system, you might have to perform nearly 30,000 GCs per second, and that's like every 30 microseconds or something, which is clearly going to be problematic. So if you're scaling the live size with some constant that doesn't depend on the number of cores, you can end up with a lot of trouble. And this is what I would think about as an error mode as well. And it's more useful, I think, to think about how much memory do I need per core in order for efficiency to look good. And for example, consider that you're using 100 megabytes per core, which is typically less than 10% of the memory availability, and add that onto the heap as you scale up. It might look something like this, that you start off with a significant part of the heap being bloated, and then as you add on a core, you're adding more bloat, but it's a relatively smaller part of the machine because we double the machine capacity. And then when we double again, we get yet more bloat, but yet lower fraction of the amount of memory being used. If we plug that into my mathematical modeling here, we find that we sort of converge to about 2.5 GCs per second instead of, I can't remember, was it 30,000 or something? So it really helps to add some amount of memory per core when you have a moving tracing collector. And another thing worth talking about is generational GC. We talked about this generational hypothesis. Most objects die young, and things that survive tend to live longer. And this is particularly useful for the moving tracing collector. Imagine that you have an application where the residency grows with the machine. It might be that you have some kind of caches, an in-memory database, or some kind of large data structure that scales with the machine. Then this can really help because most of the residency is old objects as opposed to young. And the thing about memory bloating is the amount of bloating you need to stay competitive is proportional to the liveness times the allocation rate. And that means, because it's a multiplication, that if either side here is any of the factors are small, we get a result that's small. And it turns out with generational collection, you typically get one of them being small. Let's look at an example here. So if you have a young generation, the dark purple here shows what's live, and the light purple shows the garbage. As you can see, it's a large ratio of bloat that we're adding on to stay competitive. But since the live data was kind of small, that means that the overall memory on the machine is kind of small. Whereas when the residency grows here, and is primarily old objects, then even though there's a lot more live data, the allocation rate in the old generation is much, much lower, and therefore we can get away with bloating a lot less. So in a way, generational collection really helps with the scaling here. Although there's still room for improvement here, that there is quite a bit of bloat here when you scale up the residency. But it's staying reasonably competitive, I think. Now, consider that you have an application that doesn't have some kind of cache or in-memory database or large data structure that grows and becomes gigabytes large. Then what we typically see is that the level of problem we have to solve is also quite a lot smaller. So visually it might look something like this, that we have a pretty good GC efficiency at this level, and the rest of the machine is just unused because we don't need more memory. But then if we have a deployment, we're probably gonna use it anyway, because why not? And when you do, the GC efficiency goes really low. So main takeaway here is that generational GC scales pretty well, and in particular it scales well when the problem is the biggest. So when you have a lot of residency, then it scales very well. If you don't have a lot of residency, well, it's less of a problem. So it allows residency to stay pretty competitive, even when we have a lot of objects. And because of this, all the collectors in OpenJDK are generational. Serial GC is generational, parallel GC is generational, G1 is generational, and ZGC has become generational since JDK 21 with JEP 439 that introduced a generational mode. And now, very recently, Shenandoah also integrated their generational mode with JEP 404, which I nearly didn't see for some reason. But yeah, they shipped it for JDK 25. And yeah, this allows us to enjoy the benefits of moving tracing GC while solving some of the allocation rate and residency problems you get when you scale up. Let's talk a little bit about latency as well. So latency really matters when you have an interactive application. And as it turns out, interactive applications are quite common in Java. You might have a web service, or you might have some microservice. Who knows, maybe there are games as well, or less so maybe. But basically any system that interacts with a human. There's a human somewhere that presses buttons and expects a rapid reply after that. Now these response times you get in a system like this have a sort of a distribution that can be modeled and understood with percentiles. So if you have for anyone that hasn't seen this before, P50 means essentially that if you have a P50 that is 10 milliseconds, it means that half of the requests perform at least as fast as 10 milliseconds. And P90 means that if you have 20 milliseconds, P90 means that, well, 90% of the requests respond at least as fast as 20 milliseconds, and so on. And the higher percentiles we call tail latency. Something that I think has made latency increasingly important is a trend in the industry to move over to microservices. And with microservices, you run into a situation that I call latency propagation, where for each external request that comes into the system, it calls out to like 20 different microservices. And each node along the way, if either one of them has a latency issue, it propagates across the entire system back to the external request. So if you had some kind of GC problem that caused P99 noise across these microservices, then the external request is going to observe that as a P82 problem. And if you have a P90 problem, well, then you have a P12 problem externally. So you can expect that anything that's a P90 problem is going to be a massive problem for external requests. Visually, you can look at it sort of like this. Here we have a request coming in from the left, and it calls out to a whole bunch of microservices, and all the way to the right, where you see the red arrow, there's one microservice that isn't responding rapidly, and because of that, we get problems all the way back to the external request. So what can we do about it? Well, we can either accept that the latency is bad, or we can start canceling requests based on some timeout factor that if this takes too long, we're going to have to stop it and redo the work. And redoing the work wastes CPU because suddenly you have to do a bunch of redundant work. And the other approach would be to try and improve the tail latency instead. And here's an example of what it looked like for Netflix. This was when they changed to use generational ZGC in one of their services at JDK 21. The white lines there show the error rate of their requests from the day before, and the purple stuff shows from the current day that they're measuring. And as you can see, at about 4 p.m., something like that, that's when they started using generational ZGC instead, and the cancellation rate there dropped quite significantly. And it turns out that they had a bunch of latency problems in the actual application as well that they weren't even aware of because the GC was so noisy that everything else was just not visible. Okay, so if we want to solve latency, what should we be looking for? What causes latency? And we have some usual suspects: stop the world, garbage collection, we've got oversaturated CPUs, but also startup and warm-up. And we try to solve these things as much as we can. So first of all, let's talk about stop the world garbage collection. Obviously, if you stop all the application threads, those users that I was talking about that click buttons, they don't stop clicking buttons. They continue clicking buttons while the world is stopped and requests pile up. So while the world is stopped, requests pile up, and when you start running again, you have to work through all of these requests that you haven't been handling, which can be problematic and cause latency spikes. And what you can do about it in a stop the world setting is try and use parallelism, throw as many threads at the problem as possible, and hope the parallelism scales. But it might be that the object topology doesn't allow for scaling. For example, if you have a huge linked list, that's not going to scale. You might also have problems if you have neighbor processes that you care about. Typically you don't, but in some scenarios you do. Then the noise caused by stop the world GC on the rest of the processes might be significant. Okay, let's talk about CPU utilization. That's another big factor in latency. Why does high CPU utilization cause latency issues? Well, I think it can maybe best be understood by thinking about if you go into a shop where there are 2 cashiers and there's an average utilization of 50% of the tills people go in there. But you'll find that some of the time there's no interesting activity going on, and sometimes there's a bunch of people coming in, and then suddenly there's a queue build-up. And this randomness is really what's causing the issue that latency builds up. So if you had a mental model of 50% CPU utilization looking something like this, that half of the cores are working all the time, half the cores are just idle, that is the case when you have a parallel workload. But with an interactive system, it looks a bit more like this, that some of the time all the idles are, or all the cores are idle, some of the time they're all working and their tasks queued up, and sometimes there's something in between. Overall, you get 50% utilization, but there is also a bunch of waiting involved. And there's people in queuing theory that thought a lot about this over the years and can do some mathematical modeling of the probabilities of how long the expected waiting times are, so on and so forth. Have this simple model called MMC model, where you can model if you have C different servers, what will be the expected waiting times given different utilization rates. And tried plotting this here. And if you look at the orange line there with one core, you find that the expected time to process grows quite a lot faster than all the other ones. And for every core that you add on, you get lower waiting times for the same CPU utilization. So the trend here is that the higher number of cores you have in the system, the lower the impact of the expected waiting time with a high CPU utilization. And this isn't just some theoretical mumbo-jumbo, but something that we also see in practice. So here's an example of what it looks like in SpecJBB 2015 as you increase the injection rate and the more requests being served, we can see that latency gets worse. In this case, the blue there at the bottom shows the P50, which is sort of the median, and you can see it grows with the CPU utilization. Then the green is the P90, yellow is P95, and the pink is P99. And they all sort of get progressively worse as you reach the highest level of CPU utilization. At the end, you sort of fall off a cliff. So some takeaway there is that if you have an interactive system, you probably don't want to run it on 100% CPU utilization because it will be kind of disastrous for the latency. And this is not a way that you would run things in a deployment. You would have a load balancer that scales out and keeps the overall CPU utilization much lower. Now, exactly what level you'd end up at, kind of, as I discussed, depends on, for example, how many cores and the application itself and things like that. But something much less than 100% anyway. So again, we can optimize for this, but sometimes it might be that optimizing for some kind of error mode ends up performing worse in a situation that's more realistic. So yeah, your 75% CPU utilization might look problematic on a small machine, but might look totally fine on a large machine. Yeah, and it helps to be able to scale to larger machines if you want to keep the latency low because of CPU utilization. And even on the small machines, where you have to have lower CPU utilization, it might be that you get more memory per core instead because you're utilizing less of the CPU. Okay, so since the CPU utilization is something that impacts latency, that's something that's been on our mind quite a lot, building a low latency GC, that we have concurrent threads, and if you put too many concurrent threads in there, start running concurrently, then you're increasing the CPU utilization of the machine, and the end result of that might be that you get a latency problem. So you have to really consider how many GC threads you should be using. And it turns out that if you want the maximum amount of GC throughput, meaning that you want to free up as much garbage as possible every GC cycle, then what you want to do is to wait until very late to start running the GC, because the later you wait, the more garbage is built up. But then when you start the GC late, that means you have to throw in a lot of threads into the system to manage concurrently collecting before you run out of memory. And the impact of that is you get this spike in CPU utilization, which causes tail latencies. But it's great for GC throughput. So if you want better latency instead, what you do is sort of the opposite, where you try to start a GC much earlier instead. And by starting it earlier, there's more time to perform GC. And you can run with a single thread instead, which is causing a lot less noise in the machine and it tends to go under the radar in terms of your percentiles. But it does mean that you have to spend more GC CPU cycles to get the same garbage collected. But since we have a low latency collector in ZGC, this is the approach that we've chosen. We try to use as few threads as possible and start earlier rather than later. Avoid all the CPU bursts, and yeah, make sure that latency problem is solved. Okay, so some summary here, some of the main takeaways. Maybe the most important one being that if you want impact, then try to solve things that are problems. And in order to do that, it's quite useful to think about the problems and think about the kind of deployments that people have, and whether, you know, just think about some examples at who's going to be using this feature. Is it someone deploying in a Kubernetes pod or cloud, or what kind of environment do we have? And then think about whether this solution matches that. Yeah, and try to also be wary of error modes and optimizing for that, because it might be that people don't really do that, and the thing that people do might end up getting worse. So DRAM scaling. DRAM is quite cheap, and computers get at least 1 gigabyte per core nowadays, and adding a couple more gigabytes per core is still pretty cheap. When it comes to CPU scaling, in a similar way to how you would scale the number of threads from 1 to the maximum number of hardware threads, similarly with memory, it can be quite useful to consider what happens when you use all the memory on the machine, and also consider different levels of memory scaling there with 1, 2, or 4 gigabytes per core, because that's when you can really save money. And latency, well, latency is important and something that is the driver for load balancers. And unfortunately, it's quite hard to find benchmarks where we don't try and use 100% of the machine, which makes a lot of sense for batch jobs and that kind of workloads. But for interactive systems, that really isn't what we want to be doing. So something to keep in mind. Try to use lower CPU utilization and see how does the system perform under a reasonable level of load. Yeah. And finally, the most important thing is, if we're wondering which is the best garbage collector, is of course ZGC. But apart from that, it might depend with the trade-offs and what you're actually doing. But in general, ZGC is the best. Okay, thank you very much.
Thanks for a really interesting talk.
Thank you.
Do you have any questions?
Thank you. Question from ANU. So you've been talking about giving some memory per core. I know some of the jobs that some programs do are not CPU bound. So, but in recent years, if I remember correctly, OpenJDK gained the feature of virtual thread that can run, that can do a better job at multiplexing multiple jobs into one single core. And what do you think is the impact of this recommendation if the one core can do multiple jobs at the same time more efficiently?
So my main recommendation is to look at the problems and then find a solution based on that. And if your workload has that kind of nature that it's not CPU bound, but you're rather thinking about how many VMs can I stuff into the same machine that are mostly idle or something like that, then absolutely that's worth looking into what kind of solution would match that problem.
Eros Petrang from the Technion. So you're saying it takes 10 years to build a GC and then you discover you want something else.
Yes.
Maybe it makes sense to have different kinds of GCs, and then after 10 years you discover you want something else, you have it. You just need to...
That's exactly what's happening right now, actually. Because now when people are running very small workloads inside of small containers, they're asking for something that works well on the small scale. That's sort of what we started out with, and it turns out serial GC is not too bad in those situations. And I ask people who run this kind of stuff if they have any GC problems, and turns out the main problem is figuring out what heap size to use, but otherwise they don't really have that many problems.
And what about having reference counting as another option in your,
I think reference counting is very interesting, but I think that the place for it might be not among newly allocated objects, but among older objects. But it's something that is being considered for sure, yeah.
Okay, thanks.
Hello, Jeremy Singer, Glasgow University. Thanks for a really nice talk. I think automatic memory management is becoming increasingly deployed on microcontroller devices with very constrained memory and much slower CPUs. Do you think, the numbers are different, but do you think your recommendations would be different in that domain?
Yeah, absolutely. So as I said, it all depends on your deployment situation. Yeah. And I've been mainly talking about deploying to some kind of computer. Whereas if you're deploying to some very small, like embedded device or something like that, then yeah, it very well might be that you want an entirely different solution. So you used to have a Java embedded, I suppose, and still some similar stuff going on. So yeah, definitely, if you have a deployment environment where you want very small things, then that is definitely something to consider. But you probably won't have like 32 cores running around in those controllers. So that's why it's sort of important to think not just about whether it makes sense to save memory, but about the actual scaling of CPU versus memory. And I think that still holds.
Martin Maas, Google DeepMind. Really fantastic talk. I really enjoyed this. You had this great observation about that it's not just about the absolute amount of resources that are being used, but also about the amount that's left and unused. I'm curious how you think about feedback loops. So for example, you're trying to use all the memory that's available. And then a hardware vendor might look at this and say, okay, this workload takes 1 gigabyte, let's just to be sure give 2 gigabytes. The next iteration of the workload takes 2 gigabytes. How to avoid that feedback loop?
So I don't know if it's a feedback loop or if it's just economics, that if you looked at the cost of memory versus CPU, that when you get to like 5% of the cost is memory, then even though it turns out very few people are using that extra memory, then the actual savings of not having it there isn't really that big anyway. So I think it really comes down to the economics, that if the memory starts costing a significant enough portion, it makes sense to use less, but otherwise it might not, even though it's wasted.
Makes a lot of sense. Thanks.
Thanks.
Thanks. If I could kind of following on from Martin's question, something I was reminded of. There's a very nice paper by Gernot Heiser on benchmarking crimes, and he identifies some common things that people do in systems papers in the evaluation that are like really bad. And it sounds like you've got some ideas about garbage collection benchmarking crimes, like looking at heap sizes that are not representative and looking at particular workload mixes. I was wondering if you had any specific ideas there on what we as a community should be striving to avoid doing ourselves and discourage people we see.
Yeah, certainly there's a bunch of stuff there, and I think though thinking about the memory versus CPU scaling and whether it makes sense for the kind of machine that you're running on. Like if you're running on a large machine, then it probably makes sense to use it, and if your target is something small, then you should probably be running on something small to see how it actually behaves there, instead of interpolating that it will probably be the same. and that kind of thing. But also, when it comes to the latency, to look rather at what kind of latency distribution you have at different levels of load, instead of picking one where the one you pick is the worst looking one, where the CPU is oversaturated, which you wouldn't really do. Yeah, I think those might be some of the main things to consider. I know there's difficulty also in it's not easy to write this kind of benchmarking tools and stuff, and there's always some factor of being more exact versus convenience, that you can have the most perfect system where now you're measuring every single digit perfectly, but it takes 10 weeks to run it, and it might be a problem as well. So I think I mostly have thoughts about the problem space, and when it comes to the solution space, there is definitely a bit of a trade-off there between doing it right and doing it in a timely fashion and being pragmatic.
Start at the back and go forward.
So I found your discussion of the common kind of error in research interesting, where people kind of stop after 6 times the minimum heap size. So I'm a little bit of an outsider, but I don't think that comes from nowhere. I mean, I think there was a prominent paper from a while back that where the take-home was, kind of 6 times is enough, right? You don't get a lot more performance, CPU performance, from adding more memory after that. Is that, I realize these things are often dated. Is that one out of date?
So I think, Steve, I think you were on that paper. I don't recall if the paper's main takeaway was that you should have 6 times the min heap. I think it was that you should be looking around for what the memory versus CPU trade-off is and try different heap sizes. And I think there was more of an example in that paper that it used 6 times the heap size. But I think maybe some people read that and thought, oh, so what you're saying really is that it should use 6 times the heap size, and then that's become a trend, and that's what we're seeing now. But I think that the main takeaway of, make sure that you're looking around at different heap sizes is definitely still a good recommendation. Yeah.
Thanks. And I think implicitly you're saying sometimes I do need more than 6 times to get good performance.
Yeah, absolutely you do, especially on the small scale. And on the larger scale, maybe less so because of generational collection, but on the small scale, when you have very small residency, it might definitely be that you need more, because you have to account for the allocation rate of all the cores. That might be a very large proportion to the heap size at that rate. Yeah.
Steve Blackburn, Google DeepMind. Thanks, great talk. Very interesting and thought-provoking. But I particularly enjoyed the commentary you gave about the context and how important that is. Just a very quick response if I made it to Jonathan's thing. I think partly what that was with certain algorithms, you get an asymptotic return on it for a given, and that for many algorithms would bottom out at 6x in that paper that you were referring to. But in a different context with a different algorithm, that may not be so. So I think you'd need to reevaluate it in the appropriate context.
Yeah. Yeah, I think that makes a lot of sense. And something that sometimes I think hard to talk about in an academic context is dollars, because it might be when you get some kind of asymptotic diminishing returns, that even though you have a very small amount left that you can reduce by like doubling the memory, it's without thinking about the scaling to that memory and CPU has to money, might look like seems entirely unreasonable to double the amount of memory just to use 10% less CPU. But in terms of cost, it might very well be worth it. But yeah, I don't know. It's also science, so we have to think about the resources, how they relate to each other, not just dollars. That's where I come from in industry. Think about dollars, but there's more to it.
The actual question I was going to ask, and this is very open-ended, so I don't know how you want to respond to this. In my experience, both in the academic world and in industry, I often find myself talking to people who don't want to hear about GC, who are not, they're not believers in GC, and then they will often frame their critique in terms of how a C++ program that did this similar thing would behave. Right? And then they would measure the failure of GC with respect to CPU and memory, and particularly memory, and say, oh, well, you know, our C++ runs in much tighter heap, blah, 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 blah. So at one point in your talk, I was just beginning to think, well, what would those people say to this position? And I guess that's kind of my question. Do you have any thoughts on that?
Oh, I do have thoughts. I have thoughts about a lot of things. So a different way of thinking about it, if you have a C++ program where you're able to run with only 50 megabytes, but you're still running on a machine with 32 cores, and you have 32 gigabytes of memory, then, you know, while you're using a lot less memory here, because there's no garbage, you're also inducing CPU waste every time you free memory, because when you have explicit memory management, you're paying for all the stuff you're freeing. So in a way, it's kind of a lost ability then, that you can't use the remaining machine memory that's there anyway. So you paid for the memory, it's there, and if you're not using it, it just means you're wasting CPU and freeing stuff, whereas the GC will just say, oh, whatever, let's just bloat the whole thing and just remove all the CPU overhead, and the GC is going to cost pretty much nothing, and then call it a day. So I think that there's a difference in how you look at it, that whether the important thing is bloating memory or bloating CPU. And since CPU is a more expensive resource, I tend to think that reducing the CPU is worth quite a lot more.
Yeah, totally. I totally get that. But just to refine my question, I think a lot of those folks would frame it in terms of the CPU and say, oh, the GC is really expensive with respect to CPU compared to my C++ program.
Right. And I don't know how much I can talk about this, but let's say that I've seen systems where using something like Rust or something like that, and yeah, sure, it might be that you can get about twice the amount of density in a cache, for example. And I think that is definitely an area where we can improve, is to beat native manual memory management in terms of density as you're building data structures that actually scale up to a large portion of the machine. And these kind of systems also tend to be quite costly. So even though not everything is a cache, it turns out that things that are a cache cost a lot of money when you have, like, we're talking petabytes kind of deployments. It's very expensive, and improving the density of data in those kind of deployments, I think there's a real win there if we could get that down compared to Rust and C++ and stuff like that.
Right. Well, let's thank Erik again for a really interesting keynote talk.
Thank you.
Okay, and our second presentation in this session this afternoon is going to be our Best Paper Award recipient. So very pleased to confirm that this year's Best Paper is going to arborescent garbage collection, and presenting it today will be Leonard West O'Leary. Apologies if I've not got my pronunciation as good as I could, but thank you again for choosing to submit to ISMM, and we look forward to hearing about the work.